Good morning everyone.
Good morning, sir.
So what we discussed in the last class? Structure of atom in some basic terms that we are using in this chapter right now, and also some basic atomic models also discussed, like Thomson's atomic model and Rutherford's atomic model. So today we will be discussing Bohr's atomic model. Okay, so before that you need to know two things, like light is there, na light, like light, okay, like whatever you are seeing. Okay, so it has two types of properties, like it shows wave nature as well as particle nature. Okay, so now what about wave nature? See, in the physics you are going to study like waves chapter itself. Okay, and you have separate chapters for light also. Okay, so there you will be studying about interference, diffraction, dispersion, all these things you are studying. So what that like concept saying you? So it says about wave nature of light. Interference, diffraction, all this explains what? Wave nature of light. And the next, light also shows particle nature. It is explained by photoelectric effect. What is that?
Photoelectric effect.
And black body radiations you study now. So these two things. Okay. So now let us have a look into it once. Like if you observe like electromagnetic radiation. So what is this electromagnetic radiation? It has two types of components. Like if you take electromagnetic radiations, so if this is the like direction they are propagating, it means this is the direction they are going. Okay, so now here to this direction there will be like if this is the direction, like I can say 90 degrees like this, or I can say 90 degrees like this. Okay, so there are two components, like one is magnetic component and another one is electric component like this. Okay, so electromagnetic radiations have two components, magnetic component and so now when I ask about like a spectrum, so like we have the electromagnetic radiations now. So in the different energies are there, like we have like gamma rays, cosmic rays, gamma rays, X-rays, UV rays. Okay, like this we have. So now the basic question here is, they will ask what is the energy order of these radiations. Okay, so which is highest energy here? This one, gamma rays. The next, so you just write this order. See, from that energy, like from the Planck's quantum theory we are going to discuss. Now I will give you some basic idea on that. So you are going to get a relation like this. E is equals to h nu. So when nu represents frequency, it means energy is directly proportional to frequency. Again, frequency you can write in terms of wavelength. What I am saying, in terms of wavelength. See, wavelength means very simple ma. See, if I say this is a wave, see, one wave consists one crust and one trough. So this is a complete cycle. Okay, so the distance from here to here is called its wavelength. So greater the wavelength, it means it will be occupying more position, like space. Okay, so greater the wavelength, lower is the energy or lower is the frequency. So frequency is inversely proportional to wavelength, you should say. So from here I can write nu is equals to c by lambda. So what is this c indicates here? Speed of light. So now frequency and wavelength, how they related? Inversely. Okay, so greater wavelength, lower is the frequency. So now look at these lines, I mean this energy order. So if I say energy order or frequency order, so what will be the answer? First one should be gamma rays, next X-rays, next UV, next visible, IR, microwave, radio waves. So this is the order of what? Energy or frequency. Okay, you can expect direct question on this in a very basic thing. Okay, in EAPCET we have a question on this. So if I ask for wavelength, how you will write? It will be opposite of this. So highest wavelength is for which one now? Radio wave. So now what are the rays we have? First one is gamma rays, X-rays, UV, visible, IR, microwave, radio wave. Once again, try to say 1 or 2 times so that it will be there in your mind. See one more. So now, yeah. So now, what is the order of frequency? Gamma rays, X rays, UV, visible. This is what order? Frequency order. So if I ask for wavelength, inverse, reverse. So here they have given here it as wavelength, like for wavelength. Okay, is this clear everyone? Yeah. So now when it comes to visible, again you are going to see that rainbow colors. What is that colors? Vibgyor, violet, indigo, blue, green, yellow, orange, red. Okay. So now tell me which is with the highest energy here again? Highest energy is for violet. So now which is like this is a like energy or frequency order. Okay, this is the energy or frequency order. So now which is having highest wavelength? So that's why if you observe the traffic signals or wherever there is a danger signal, they will use red color because it has greater wavelength so that it can easily visible to the longer distances also. Okay, this is the main reason. So now at least with this application you should remember. So why we are using red color for danger signals? Because it has greater wavelength, easy to see that. Okay, so that's why it is used. Okay, you can remember in this way. So which is having highest frequency or energy? Violet. Lowest is for red. If I ask in terms of wavelength? Yeah, that's it. You remember it like that. Okay, right. Then next. Yeah, up to here it is clear now. See, you are going to answer this question now. So tell me the radiation with maximum frequency. As per that. Now my question is arrange them in the increasing order of frequencies. X-rays, okay, is this clear everyone? Yeah. So the next one, try to read this question once. An element in +2 oxidation state has 24 electrons. See, an element X I am saying, X is an element. How many electrons it has? 24 electrons are there when that element is in which oxidation state? +2 oxidation state. If it is in +2 oxidation state, it has 24. Now, if I take its atom, so atom means 0 charge on it. Are you following everyone? Okay. So now how many electrons should be there? 26. Okay, up to here it is clear. Now read the remaining question. The atomic number of element and the number of unpaired electrons in it respectively. So what is the atomic number of that element now? 26. Is this fine? 26 here we have and here we have. Now what is the next question they are asking? Number of unpaired electron. So atomic number 26, what is that element? Iron. So Fe. So what is the electronic configuration? See, I told you that mnemonic also, like easy way to give the valence electronic configuration. See, 26 means argon 18 over. Okay. See guys. already I told you at least you need to know 30 elements or even you can also learn that full periodic table also I given. Okay, see, don't think that if sir is explaining something means the by default it goes into your mind. You have to put some work from your side, then only you can get that. Okay, it's not like something you are buying from outside and wearing it like a shirt. Okay, so now 26 means I have written argon as 18. After argon what, how many numbers we need to write? See, after this, like see 26 I have now, so 4s, 2, 3d, 6. So 18 plus 2, 20, 26 is over. So now s orbital electrons are fully filled. Now what about d orbital electrons? Like this you write, 5 orbitals are there, na, d orbitals here, 1, 2, 3, 4, 5, 6. Now how many unpaired electrons are there? So n is equals to 4. Okay, so what is our answer? B. That's it. How easy it is? Yeah. So yesterday we did this question, you told this as isotonic. This isoelectronic species also we did this question in periodic table itself. Okay, next. Black body radiation, again the same thing you are going to study in what is it, physics. Okay, so now what is this? I just give you some basic idea. I don't want to go in detail because there you will study something like Wien's displacement law. Okay, so there you will study along with that. See what they are saying, ideal body, black body means what? An ideal body which emits or absorbs all types of radiations at all frequencies. So those bodies are considered to be so now in reality there is no, see there is no nothing like black body, there is nothing like ideal gas, ideal body, nothing like that. We are expecting something to be ideal and we are relating the natural things, the real things to that ideal one. Okay, like we are also taking someone as inspirational, like he is an ideal person and we are also trying to be like him right now. So this is how the motivation gives the motivation and all right now. So we are considering someone as ideal and we are relating to him, so we need to be like him, like that we are see. Okay, so here also same thing. Now here you just remember that how intensity varies with the wavelength in case of ideal bodies. See, if you increase, see this is at T1 temperature, this is at T2 temperature. See, intensity increases with wavelength, okay, reaches maximum, then decreases. Now this is a temperature T1, this is a temperature T2. So with increase in temperature, what happening to that peak you are seeing? See, peak is moving towards lower wavelength side. See, intensity peak, this is the maxima peak now, intensity peak, here it is maxima, here it is maxima. I am saying T2 is greater than T1. So now what is happening with increase in temperature? That peak is moving lower side of wavelength. So peak is moving this side, now this side if you goes higher wavelength. So peak where it is moving? You just remember this, we will discuss again. Okay, so now Planck's quantum theory, what this Planck's quantum theory says, tell me? See, if you take any substance, like any like hard body if you take, so now it will emit the energies. What it will be doing? It will emit the energy in the form of small packets. Okay, if you are taking any black body or something like that, so what happens from that, if you are heating that substance, what it will do? It will emit some energy or not? We are observing in our daily life also, if you are heating one hot material like iron rod, what it will do? It will also emit some energy or not? We cannot even able to touch it. It means it is emitting energy or not? Whatever the energy you are sending to it, is it keeping itself or it is emitting? So that emission of energy happens in the forms of small packets. What is that? Small packets. These small packets in a discontinuous manner. Okay, so those are called quanta. What is that? Those are called quanta. Okay, so now I told you in the form of heat. So normally we are talking about light now. So the quantas are called, when I say light, the quanta, whatever the energy is released. If I use the light, that energy, light also releases energy now, that you should call it as photons. What you should call? Photons. Okay, so now here energy of each quanta is directly proportional to its frequency. What I am saying, energy is proportional to frequency. From here I am removing this proportionality and writing h, nu. Okay, so here nu represents what? E represents, H represents Planck's constant. What is its value? 6.6 into 10 power minus 34 joule second. What is that? 6. You need to remember this value. How much it is? 6.6 into 10 power minus 34 joule second. Okay, remember this. Now, yeah. So now the question will be like this. Simple way they will ask you one question. See, a wavelength of the light is given. Then they will ask you find its energy. See what I told you, there are VIBGYOR colors, or there is X-rays, gamma rays, UV rays, like that we studied. So every ray or every wave will consist of some energy right now. So now what is the energy for this particular wavelength, they will ask you by giving you something like this. See the question here they have mentioned, calculate the energy of a given photon, wavelength this much and this much. Two questions are mentioned. So now here what is this law, like this one is called Planck's quantum theory. So you got E is equals to H nu. So here in the place of frequency I can also write C by lambda, because frequency is equals to C by lambda. So what is this C called here? Speed of light. How much it is? 3 into 10 power 8 meter per second. Okay. So these small values, these constant values you should remember. Okay. It will be useful for both physics and chemistry. Okay. You are going to deal more in physics than this chemistry. Okay. Up to here it is clear now? Yeah. So now my question is, this is a story when I am saying about one photon. What is that? If there are n photons, n into this number right now. So you should write E is equals to n h c by lambda, or E is equals to n h nu. See, E is equals to h nu is for one photon. For n number of photons, n h nu. That's it now. Okay. So these are the two relations you should remember here with these constant values. Okay. Now try to solve one question. I am giving you lambda is equals to 3000 what is that? 3000 angstroms. 3000 angstroms. Then what is its energy, or energy associated with this wavelength? How can you do that? So 1 angstrom is equals to 10 power minus 8 centimeters. How much? It means which is smaller here, centimeter and angstrom? Angstrom is very small. Okay. Next, this will be also written as 10 power minus 10 meters. 1 angstrom equals to how many meters? Minus 10 meters. Now try to substitute over here and get me the value. Energy, how can you do this? E is equals to h c by lambda. So now what is h? 6.6 into 10 power minus 34 joule second. Okay, into c. 3 into 10 power 8 meter per second. And next lambda is how much given? 3000. So 3000 it is meters. Here it is. So 1 angstrom, how many meters? So in the place of this thing, what I can write? 10 power minus 10 meters. Can I write it like this or not? Yeah. Up to here it is clear. So now this meter can be cancelled out. Okay. The next one is here 3 is there. Here also 3 is there. Okay. Next one is here second is there, second inverse is there. So I can remove this also. Yes or no? Yeah. So now what is the units we are remaining with? Only joules. Yeah. What is the units for energy? So we are getting proper answer only now. Okay. So now here 10 power 3 is there, 10 power minus 10 is there. So this can be minus 10 minus 24. We can cancel them now. How many times it becomes now? 10 power minus 24. Okay. The next one here 10 power 3 is there. Here 10 power 8 is there. So 10 power 5 can I try? Yes. Okay. So now what is the answer we are remaining with? 6.6 into 10 power 20 minus 24 plus 10 power 5 is there. So minus 24 plus 5? So 10 power minus 19. Okay. 19 joules. This is minus 24 plus 5. How much? Are you getting this what we are doing? Yeah. So this is your final answer for this question. Everyone got this? Yeah. So can you do the same thing when I give lambda is equals to 6000 angstroms? Fast, fast, please. Yeah, it's very easy. Here I am saying 3000, here I am saying 6000. You take here 3000. Now I am saying 6000 now. So just into 2 here you did, it means the denominator is 2 is there. So cancel out. 6.6 by 2 means what? 3.3 into 10 power minus 19. Everyone got the answer? How much is the answer? 3.3 into 10 power minus 9. Array, see, when you okay, done up to here. We'll see next slide how. Okay, fine. Up to here it is done now. Yeah. Anyways, you did this on your own. Next question is. Yeah. So the next topic is photoelectric effect. What is that? So what this photoelectric effect says? Tell me. Anyone have any idea on this? See, if this is a metal surface, what I am saying, if this is a metal surface, now see, metals are electropositive or electronegative? Electropositive. It means whenever something is happening, first they will try to lose their electrons. That is what do we mean by electropositive means what? They easily loses their electrons. So now what I am doing is, I am using some energy, some suitable energy, and that is incident on this metal surface. Okay. Now what happens on metal surface? Metal atoms are there now. Okay. So from that metal atoms, what happens when this energy is striked? Okay. So whatever the loosely bounded electron is there, that will comes out. Yes or no? See, if this is a metal surface having one electron, so now I am supplying some incident energy, I am incidenting energy on it. What happens? See, this electron having some 10 electron volts of energy. How much? Now I am supplying some 15 electron volt of energy. How much I am supplying? 15. So whatever the energy I am supplying, it is more than its requirement now. So now what happens? It will pick out that electron. Okay. So this process is called photoelectric effect. But if I am supplying only 5 electron volts of energy, will this electron comes out? No. It means photoelectric effect won't be absorbed in that case. Okay. Not seen in that case. Okay. So now what you are doing? You are supplying some E amount of energy. Okay, some energy is supplied, E amount of energy you are supplying. Now, some amount of energy from your supplying energy, some amount of energy is utilized to take out that electron, that photoelectron, right now. So that energy, whatever you are using to remove the electron from a metal surface is called work function. What is that? Work function. So now, first case, how much energy I supplied? 15. But how much energy they required? Just 10 electron volt is required. But I supplied? 15. After using 10 electron volt, electron comes out. Remaining how much extra is there? 5. That 5 electron volts will be taken by that ejected electron. See, I am supplying a photon here having energy 15 electron volt. This electron to come out from the metal surface uses 10 electron volt. After coming out that electron, how much extra energy is there still? That 5 extra electron volts will be taken by this photoelectron only. Okay. Now what it will do by taking that energy? Yeah, it will convert into its kinetic energy. Means it will move here and there. Okay. So now the energy you have supplied is like dividing into two parts. One is to eject the electron and another one is to convert into kinetic energy. So E supplied will be equals to work function plus kinetic energy of that photoelectron. Is this clear? What I am saying? See again, 1 electron requires 10 electron volts of energy. Okay, how much energy I am supplying? 1 photon, that photon means one particle that will hit on the surface, 1 electron comes. So every time you remember, 1 photon will eject 1 electron. What I am saying? So if I say that, sir, photon is having some 30 electron volt, it doesn't mean it will eject 3 electrons. 1 photon will eject how many electrons? 1 electron only. Whatever the energy it has, how many electron will be ejected by 1 photon? 1 electron. Yeah, just remember that. Sir, it requires only 10 electron volt now. It means we can eject 3 electrons with using 1 photon means no, it is not like that. 1 photon will eject how many electrons? 1 electron, whatever may be the energy difference there. Okay, is that clear? That is important point. So E supplied is equals to work function plus kinetic energy. See, work function is nothing but small energy only, na, that is also, this is energy, this is also energy. But to make some difference, I am writing E is equals to h nu here, and here I am writing h nu naught here. Okay, and kinetic energy what we will write? Half mv square. Okay, so now here nu and nu naught, nu represents what? Frequency. Okay, and what about this one? Threshold frequency or the work function you are saying, na, this one. So this is should be called as threshold. Threshold means what? The minimum frequency that must be supplied to see this photoelectric effect. Okay, now if I applied, if I say applied frequency equals to threshold frequency, now what happens to kinetic energy? Kinetic energy, no, zero, no, because whatever the energy I am sending, it is equals to the energy required for electron. So 10 electron volt required, I am also sending 10 electron volt. So there is no kinetic energy. So if this is the case, Ke is equals to 0. And one more thing, if nu is less than nu naught, will the photoelectric effect takes place or not? So I can say no PE, no photoelectric effect. If nu is greater than nu naught, yes, photoelectric effect takes place, and there is some kinetic energy for the photoelectrons also. These are the three possible ways you can understand this. Okay, now next one here is, let us see some questions otherwise. See here what they are saying. Calculate the frequency and wavelength of photon with energy this much. What you will do? Calculate the frequency and wavelength of photon with energy this much. Energy is given and they are asking us to calculate. What is the relation between them? E is equals to h nu. What they are asking us? Frequency. So what will do? E by h. So now try to do that. Finish it fast. Please do it fast. So how can we do this? 3.98 na, so 3.98 into 10 power minus 15 joules. Energy is given like this. What about H value? 6.6 into 10 power minus 34 joule second. What is the units for Planck's constant? Remember them. Okay, so this you can remove. And here, what they are saying, frequency and wavelength of photon with that much energy. Yeah. So here, how many times this one? So like you can remove now this one how many times? So 20. So 10 power minus 19 is remaining. So I can write this as 6.66 is how much? Once check. 6 6 6.6 means around 39 you will get, 39.2 like that, 39.6 you will get. Okay, see this number 3.98, what we have now, here see, 10, so can I write in the numerator as 10 power plus 19 by 6.6, yes or no? What is the units we have? Second in the denominator, so second inverse. Okay, see minus here plus 19 is there now, so I can write this as 18, so that I can use 10, becomes 39.8. So this many, how many times it is? Around 6 times. So 6 into 10 power 18 second inverse. Everyone got this? How we are doing? Yes. This simplification. Calculation unable to follow? Array 3.98 into 10 power minus 15 joule second is there. Here 6.6 into 10 power minus 34 joules is there. 34 joules is there. So joule can be removed. Okay? Joule can be removed. Next what we have here, minus 15 minus 34, how much? Minus 19. So here in the denominator minus 19 means here I can write plus 19. Up to here it is clear. So 19, 10 multiplied with 10, like that how many times it is? 19 times. So I can write it as 18 times and I am multiplying 10 with this one. So what it becomes now? 39.8. So 6.6, 6 are how much? So it is around 6 times now. So 6 into 10 power 18 you have finally. So second inverse. Second inverse is the units for frequency. Okay. Next, how do you calculate wavelength? Frequency we got now. So from frequency what is the relation? C by lambda. Now I want lambda means C by, now tell me fast. 3 into 10 power 8 meter per second, and in the denominator frequency how much we got?
6 into 10 power 18.
Second inverse. So second inverse cancel. Okay. So this one 8, 18. So 10 power 10. So 10 power 10 is plus here. If I write in the numerator, 10 power minus 10. So this one how many times? 3 2s are. So you have something like 1 by 2 into 10 power 10. 1 by 2 into 10 power minus 10 meters. This is wavelength. Yes or no? Up to here is this clear? Okay. So 10 power minus 10 meters means can I write in angstroms? So 10 power minus 10 meters is 1 angstrom. So you can write it as 0.5 angstroms. Is this clear everyone? Yeah. So we have which option here? First option. So can you go with the second question? What is that second question says? Everyone please try to do that. What is the work function of the metal whose threshold frequency is this much? See what to do? Work function is nothing but energy only now. But we are representing that with like omega naught. Okay, this is nothing but it is also energy like nu naught. Yes or no? Photoelectric effect what we studied? E supplied equals to work function plus kinetic energy. So now this work function is nothing but energy only I told you. So that is H nu naught. Now what they are asking you to calculate, what is work function? So H into nu naught you do. So nu naught is given, multiply with H, you will get the answer. Okay, once try it everyone. I will be checking now. Once try it everyone. Next one is here we have like this now. Next one, see with this kinetic energy, what that electron will do? It will move here and there right now. So now there is something called stopping potential. What I am saying? Stopping potential means what? That electron should not be moved anywhere. Okay, it means the opposing potential that must be applied to make the photoelectron velocity as 0. It means this value should become 0. This value should become 0. It means kinetic energy is equals to stopping potential. Stopping potential. Then it will become 0. So stopping potential, I can write potential charge into potential. Okay, which is equals to half mv square. So if they ask for stopping potential, you can do it from kinetic energy, or they can ask you kinetic energy, do it from stopping potential using this formula. Okay, then the remaining things you can discuss in the physics. If not, I will only explain based on your approach towards the questions. You practice some questions, you come to me, we will discuss further. Okay, the next, yes. Once read that statement, ma'am. The minimum opposing potential required to stop the photoelectron. See, you are writing it as h nu equals to nu naught Ke. With this Ke only that electron is moving now. So if you make this 0, it won't move. So that is what? The minimum potential energy, that is equals to this kinetic energy, makes it to be 0. So I can say K is equals to stopping potential. So stopping potential you can write in terms of potential, like charge into potential. For electron there will be charge now. So E into nu, like this is potential symbol, and here kinetic, like kinetic energy. So you can use half mv square also there. Okay, that's it. Next, we will be discussing about Bohr's model. See, on photoelectric effect, we can also discuss few more questions, but we have very less time actually. Do it fast. What they have mentioned, work function values for 6 metals were given. So these are the work function values for metals. Work function value means what? That is the energy required to eject the electron from their metal surfaces right now. So now how many of the above metals do not eject the electron when they are made strike with radiation of wavelength 400 nanometers. So now, but here the values are mentioned in terms of electron volt. So now how can we do this? Yeah, I will tell you one simple formula, you can use that. See, when they are asking about the energy, you can use this energy in terms of what they are asking, in terms of electron volt. You just use this energy is equals to 1240 lambda in nanometers. Okay, so what is the answer you are going to get? 1240 by how much? 400, 400 nanometers. So 0, 0, here 0 means 12.4, okay, and this will become how much? 3.1. So now what is the energy associated with this wavelength? What is the energy associated with that wavelength? 3.1. So it means if you are supply this much of energy, this much of frequency or wavelength to the metal surface, how many electrons out of this will be ejecting or showing the photoelectric effect they are asking, or not showing the photoelectric effect they are asking. See, this is the minimum energy you are supplying. So tell me, will it eject the electron? eject the electron or not? See, E supplied is equals to, what is that formula? E supplied is equals to work function plus kinetic energy you are writing. So when the photoelectric effect is seen, when your supplied energy is greater than, so how much energy you are supplying? 3.1. So what their work functions given? So this is 2.4. So is this less than that or not? Yes. So less than that means whatever the energy we are supplying, is it sufficient or not? Yeah. So will it show the photoelectric effect? Yes. So what about this one? No. It is 3.1 only we are giving, but it requires? So it won't show. Next, what about this? No. What about this? No. What about this? Yes. What about this? Yes. Now what they are asking us? Do not eject, do not show the photoelectric effect. Who are those? 1, 2, 3. So magnesium, copper, silver. So answer C. Is this clear, everyone? Yeah. So what is the important formula to be remembered here? Previously you have remembered that energy in terms of joules. What is the formula you used? E is equals to h nu or hc by lambda. Here if I ask in terms of electron volt, 1240 by lambda in nanometers. Till now, most of the students here are just they are habituated for descriptive writing, like IPE exams only. Here most of them are very new to problem solving, like if I give a question and they are taking too much time for simplification. So how can you overcome this? You practice more number of questions. That is the only way you can do it. Otherwise, for one question, some people can solve in 1 minute and some other can taking like 5 minutes, 10 minutes also. If you take EAPCET exam, how much time you have for one question? 1 minute. Hardly 1 minute 20 seconds, like that only. Okay, so it is very difficult if you spend 10 minutes, 5 minutes for one question. So practice more, you can maximize your score. Okay, that is the only way you can do. Next, okay, we'll go with Bohr's atomic model now. See, I will tell you Bohr atomic model in the simple way possible. Try to listen. See, what is the drawback of Rutherford we discussed yesterday? He was unable to explain the stability of electron. And the next drawback also I told you, spectra of the atomic spectra is not explained, we have discussed. Those drawbacks, he utilized that theory, and looking at the drawbacks, he proved his, or he given his model. Who is that person? Bohr. Okay, so what he told, see, when he is proposing his atomic model, he given some postulates. Okay, he considered some points. What are those points? Atom is considered to be spherical in shape. What he told? Atom is considered to be spherical in shape, in which the electrons are revolving around the nucleus in circular paths. What he told? Electrons are revolving around the nucleus in circular paths. Okay, those circular paths like this. So these circular paths are called orbits. What those are? Orbits. Okay, so now these orbits have fixed energies. What they are saying? These orbits have fixed energies and fixed radius. It means if this is a nucleus, from the nucleus to here, there is some fixed radius r1, I can say. Okay, from here to here it is r2. Like that, whatever the orbits you are taking, they have fixed energies or not, fixed radius or not. Yeah, so they told these orbits have fixed energies, and if they have fixed energy, they can also be called as stationary states or stationary orbits. Stationary states or stationary orbits. Okay, is this clear up to here? Next, now these orbits given with some numbers like n equals to 1, n equals to 2, n equals to 3, or it is represented with k, l, m, so on, like that. Okay, later we called these numbers as what? Principal quantum numbers. See, I don't want to write all the theory point. Are you able to follow me? Yeah, we already you have books. Same lines it will be there or it will be there in the next slide also. Okay, but try to understand the concept that we are discussing. First point is what? Electrons are revolving around the nucleus in so those circular paths are called orbits. So orbits have now fixed energies and fixed radius. Okay, therefore they are called as stationary. So now they are represented with numbers 1, 2, 3, 4 or K, L, M, N. So those are called as shells. What is that? Shells. Okay, yeah. So these numbers are called principal quantum numbers also we discussed. Now only those orbits are allowed in which whose angular momentum is quantized. What I am saying? It means, see, if this is a center, from here, if let us say here electron is present, okay, so now electron is revolving around the nucleus in the circular path now. Yeah, in order to accept this circular path, its angular momentum must be quantized. So what is this angular momentum quantization means? See, angular momentum I am indicating with symbol L. So its value should be equals to NH by 2 pi. How much it should be? NH by 2 pi. So now let us come to a little bit about physics. See, if I am saying this is a positive charge and this is the orbit. Electron is present over here. Are you able to see from the last page? This red color is able to see properly, or I should change the color? Yeah. Okay, so now what this electron will do? It will be revolving around the nucleus like this. Yes or no? Yeah. See, it is making some theta with this radius if you see. Okay, so here distance r it is moving, making some theta. So now angular momentum L is equals to, you should say it as m v r sine theta. What it is equals to? M v r sine theta, where mass is a m is a mass of electron, r is a radius from center to the electron, that distance. Okay, the next v is the velocity of that electron, and theta here it is making some angle now. So sine, how much theta it is? 90. So now what happens here? MVR sine 90. Sine 90 is how much? Sine 90 is 1. So angular momentum L equals to MVR it becomes. Okay, so now this value should be equals to this one. So I can write MVR equals to NH by 2 pi. So this is the most important thing you should remember here. MVR equals to NH by 2 pi. So now R means what? Radius of that orbit in which electron is present. So electron may present in first shell, second shell, say third shell, like that. So I am generalizing it as MVRN. N indicates shell number. 1 it can be, 2 it can be, 3 it can be. It cannot be 0. Okay, is this clear everyone? So up to here is this clear? Okay. Now here if you observe, we have mass. Mass of electron is fixed now. How much mass of electron? Mass of electron, how much is the value? Yesterday we discussed now, 9.11 into 10 power minus 31 kg. So this value you should remember now. Mass of electron means. Okay. Next, N can be what I told you, it can be 1, 2, 3, 4, so on like that. Whereas H is what? Planck's constant. So its value also we know, 6.6 into minus 34 joule seconds. Okay. So now what are the two other variables we have here? Pi is a constant, we have some value for it. Okay. Now here velocity we have, radius. So now using this equation we are going to calculate radius of an orbit in which electron is present. What we are going to calculate? In which the electron is present. See, it has some simplification, some steps are there. So I am not going to discuss that. I am directly giving you the formula. So how can you calculate that radius? So radius of an nth orbit is equals to, you can take, see, R means what I can write? NH by MV I can write now. Like that, see, N is a constant, H, all these are things like h is a constant, pi is a constant. If you put all those value upon simplifying, you are going to get a radius of an nth orbit as 0.529 n square by z in terms of angstroms. What is the value you are going to get radius? 0.529 n square by z. So what this n represents? Shell number. Z represents? Z represents what? Atomic number. Atomic number. Okay. So yeah. So this is about radius. Okay. I will tell you about velocity also. Okay. Then next one. What are the postulates I told you? Electron revolves around the nucleus in circular paths. Okay. So they have fixed energy, like that we discussed. Next one. He told that electron, when it is revolving in the shell in these certain circular paths, it will not emit energy or it will not absorb. What he told? If an electron is revolving in this allowed circular path, it will not emit energy or it will not absorb energy. But in case if it is emitting any energy, what I am saying, in case if it is emitting any energy, then that electron emitting energy means it is losing the energy now, it will go and fall into the lower energy level. For example, electron is at here, electron is at here. So now if it is emitting energy, where it will go? It will comes to the next lower energy level. Okay, like that. Or other ways, if an electron is absorbing energy, what it is? Electron is absorbing energy. Now what happens? Electron will goes from lower energy to higher energy. So this says about emission of energy and absorption of energy. See, the emitted energy corresponds to emission spectrum. The absorbed energy corresponds to absorption spectrum. So from this postulate, we got to know that emission and absorption spectra. Is this clear? So now he got overcome with the drawback of Rutherford. Next one. What about stabilities are you might be having? So how we are going to calculate the stability means, see how he explained is, here electron is revolving between electron negative charge, nucleus positive charge. What they have? Attraction forces. So now that electron will attract it towards the nucleus like this. Yes or no? That is attractive force. Now you just imagine electron is revolving here now. You just imagine you have a thread like a rope. One end of that rope you are tying one stone. What you are doing? Stone. Now you are like rotating it like this. Now if you release it from your hand, where it will goes? Goes away from you or comes towards you? Away. So it goes away from you. The first one what I told you, that nucleus will attract the electron. See, if these both forces are equal, what happens? Electron won't go anywhere, it will stays in that path only, right now. So using this explanation, he told it will be in a stable form. Means what he told, that centrifugal force and centripetal force are equal, so this is the reason for its stability. Okay, so now we got explanation for stability and spectra. Okay, so from that stability relation only we are going to calculate this radius, energy and all those things. Okay, right. So this is about radius formula I have given. Now one simple question I will ask you. Okay. Between electron and proton, what they have? Between proton, nucleus and proton, electron, attractive force. So it means from here orbit, electron will be attracted towards the nucleus. So that is attractive force. If only attractive force is there, directly electron fall into the nucleus and it will destroy. Now what he told, along with this attraction force, there is outward force. This is called inward force. There is one more force, that is outward force. Like you are spinning a like stone using a rope. If you release it, it will goes outward now. So that outward force and this inward force will be equal. So that makes it to be stable. If any force is extra, it will get destroyed. But both of them are balanced. So based on he explained the stability. Okay, got it? Yeah. Next. So radius formula you got. So now a simple question I am asking, what is the radius of first Bohr orbit of hydrogen atom? What I am asking, what is the radius of first Bohr orbit of H atom? Tell me. So how can you calculate this? N is 1, 0.529, n square, n is how much? 1. Hydrogen atom atomic number? 1. So 1 by 1 angstroms. So you should say this as 0.529 angstroms. This is R1. Similarly, if I ask you what is the second Bohr orbit of, what is the radius of second Bohr orbit of hydrogen atom? 0.529 into 2 square, it should be 4 by 1. Is that clear? Okay. So now R2 of hydrogen atom, if I say, how you will calculate? 0.529 into n square. N is how much? N square. Second I am saying 2 square, that is 4 by Z, atomic number for hydrogen atom 1. So you just multiply this, you are going to get second Bohr orbit. So if you see the values, this is 0.529, this is 0.529 into 4. So what happening as n value increases, radius also increases. See, it is increasing or not? Yeah, like that you can say. Okay. So for an atom, radius of nth orbit of hydrogen is equals to radius of first orbit of hydrogen multiplied with n square. Can we make it like this simply? One small relation. Yeah. The next one, can you try what is the radius of second orbit of helium ion? Tell me fast. Second orbit I am saying, see, it's very simple, ma. Try to make it like this. What I am asking? Second orbit. So you write Rn, n value you put 2. For which atom I am writing? Element, which species? You write it here so that you won't get confused. Helium. Okay, is equals to 0.529 into n square by Z, na? N square by Z. So what is the n value here? Rn. N is how much you put? 2. You put here 2 square. So 2 square. And what about Z here? Helium ion? 2. So 2. So 2. So it will be 0.529 into 4 by 2. So that will be 2. So like this you can calculate radius like this. Is this clear, everyone? Yeah. Next one. Next formula is about velocity. What is the radius formula you got? N square by Z. Next one is what? See, you are going to solve many questions related to this now. Okay. Now see here, what is the next one? What is that? Velocity. So how you are going to do this velocity? See, the formula here comes is V is equals to 2.18 into 10 power 6 Z by N. What is it? Z by N. So this is in meters. When meters per second. Velocity means meter per second only, no? Yeah. See how we got this formula. What is that important equation I told you? MVR equals to 2 pi. So from this we need what? So what you can write? NH by 2 pi into R. So radius formula what we got? 0.529 n square by Z. Okay. So I am trying to put over here 0.529 into n square by Z. So can I write this Z in the numerator? Yeah, Z is writing over here. Now see, n here and n here. So can I cancel out this n and this n? Now what we have here? H by 2 pi m into 0.529 here multiplied with Z divided with n. See, these are the only two numbers that changes. Z means it depends on atom. If it is hydrogen atom, 1. Helium ion, 2. Like that. N value depends orbit shell number. 1, 2, 3. So these are only variables, all these are constants. Constants only or not? This one, h, all these things. So if you put all these values, mass of electron, pi value, h value, upon simplifying, you will get the value as, how much I told you, 2.18 into 10 power 6 z by n meter per second. So this is about velocity of electron in an nth orbit of hydrogen like species. What is the formula here? Again tell me. Try to say it 1 or 2 times so it will be there. Yeah, done. Next, try to calculate velocity of electron revolving in the first orbit of hydrogen atom. What I told you, velocity of electron revolving in the first orbit. N value is how much? 1. Which atom? Hydrogen. Here also? 1. So both 1, 1. So you are remaining with this value. Is this clear? Yes. Okay. So now what is the final answer? This one you will get the answer. So now velocity of electron revolving in the second orbit of helium ion. Yes. Velocity of electron revolving in the second orbit of hydrogen atom. Second orbit of hydrogen atom. Yeah, second orbit of, so try to catch me all the time. Second orbit of hydrogen atom. So V of 2. 2.18 into 10 power 6 into Z. Z is how much? 1 by 2 meter per second. So this will be cancelled out like 1.9 into 10 power 6 meter per second. Everyone clear with this formula? Yes. Now they will ask you one question. See, what is the velocity of electron revolving in the first orbit of hydrogen? Tell me. (10 power 6 meter per second. Now velocity of light is how much, you tell me? 3 into 10 power 8 meter per second. So now simply they will make you one question. See, the same question can appear in physics also. What is the relation between velocity of electron to the velocity of electron that is present in the hydrogen first Bohr orbit to the velocity of light? How can you relate this? Velocity of light to the velocity of electron in the first Bohr orbit. What to do? Take the ratio of these two values. So how much? This value by this value. Upon simplifying, you are going to get, it is 137. Approximate value. How much? 137. So velocity of light is equals to 137 times greater than velocity of electron in the first Bohr orbit of hydrogen atom. Do you got what I am saying here? Which one is more velocity here? Electron or speed of light? How many times? 137 times of the velocity of electron in the first Bohr orbit of now they not only ask about first Bohr orbit, I given you as a first Bohr orbit. If I ask you second Bohr orbit, what you will do? You calculate the velocity of electron in the second Bohr orbit, take that value in the denominator, speed of light in the numerator, try to cancel out, you will get the value. Are you able to like connect to this or not? Once again I will tell you. What I am asking, velocity of light is how much? 3 into 10 power 8. Velocity of electron in first Bohr orbit is how much? 6. What is ratio in the adugutunna? How much that ratio will be? 137. So what it is saying? Velocity of light is equals to 137 times velocity of electron in the first Bohr orbit of hydrogen atom. This is the final outcome that you should remember. Okay, so how we got 137 means? Ratio of these two numbers. Okay, That's it. Clear everyone? Or having any doubt? See, you should feel free to ask again. Next. Velocity is over. Next. Radius is over, velocity over. Next one is energy. Next is what? Energy. So here try to look at here. If this is nucleus, what I am saying? So electron, see, if this is a positive charge, somewhere at infinite distance electron is there. What I am saying? Somewhere very far one electron is there. So here one electron is there. You consider this as infinite distance, somewhere electron is there. So infinite distance means, is there any attraction between them? No. So at that state energy is equals to 0. What I am saying, energy is equals to 0. Now you are trying to bring that a negative charge little closer to the nucleus. It means positive charge. Now what happens between nucleus, positive charge and negative charge? Attraction. So as you bring that close to the nucleus, what happened? Stability of that charges will be increased. Stability of that system will be increased. So now as you bring it more closer, so as you bring it more closer, what happens? Stability of their system increases. So when stability of a system increases, its energy decreases. It means when you are bringing it closer, energy becomes negative. What happens? Energy becomes negative. Now the formula of energy will be like this: E is equals to minus 13.6 into Z square by N square electron volt per atom. Electron volt per atom. What is that? Once again you tell me.
E equals to minus 13.6 into
Z square by N square. So now you try to calculate it for what is the energy of electron that present in the first Bohr orbit of hydrogen atom. Minus 13.6 into Z value is how much? Hydrogen atom is 1. N square now, 1 square here, 1 only. So this will be electron volt per atom. So how much you got finally? Minus 13.6 electron volt you got. So now energy of electron present in the second Bohr orbit of hydrogen atom. Tell me. Same. How can you do this? Minus 13.6 into hydrogen atom. 1 by 2 square na 4 electron volt per atom. Now try to simplify this. 3 ones are 3 4s are 12. 1.6 is there. अरे यार okay 3.4. So how much you got? Minus 3.4 electron volt per atom. Okay, so now you do it E3. Yeah, E3 you do it and tell me. Energy of third Bohr orbit of hydrogen atom. Tell me. Tell me first, how can I do? Minus 13.6 H Z is 1 by 9 electron volt per atom. See, 9 ones are 4.6 is there. 45 is a 9 5 is a 45. So 1.5 you got around. So you got minus 1.5 in 5 electron volt per atom. So this is for E3. So now what you are saying? See, this is 0. What is the first energy we got? Minus 13.6. Second energy what? minus 3.4. What is the first energy you got? I mean E3 got equals to 2, n equals to 3. How much we got here? E3 minus 1.5. So as you increase the n values, what is happening to the energy? It is going towards or equals almost nearest to the 0. Yes or no? See, as you increase the n value, shell number, means you are going away from the nucleus. See, n equals to 1 means if this is the nucleus, n equals to 1 means this shell only now. N equals to 2 means this one only now. N equals to 3 means again bigger one. It means as you increase the n value, radius increases. What about its energy? Energy also increasing, you should say. See, minus 1.5 is bigger or minus 13.6? Minus 1.5 is bigger. Okay, so it means as n value increases, energy increases, and maximum energy when n equals to infinite, you are going to get 0. So you don't have positive values here, you have only negative values, and if infinite is n equals to infinite, you are going to get a 0. Is this clear, everyone? Okay, so what is the formula to be remembered here? Yeah, next. So you got this now, energy values. What is the ground state energy we got for hydrogen atom? Minus 13.6. So now second state, how much you got? N equals to 2. Minus 3.4. If you go little more higher, 1.51, minus 1.51. As you go upside, like n equals to 4, it is minus 0.85. Little more higher. Like that, we are moving up to infinite level, you consider. Okay, infinite level energy is how much? 0. So now what happens as n value increasing, energy? As n value increases, energy also increases. So remember, again energy, n value increases, energy also increases. Up to here it is clear. But if you observe, energy gap between two energy levels. See, energy gap between two energy levels. See, for first one and second one, this much big gap is there. But second and third level, it is very small. As you move away upside, the energy gaps are becoming small. So it means if you go for infinite level, they are almost like very close like this. Yes or no? So as you make one statement now, as n value increases, energy increases. But energy gap between energy levels decreases. So which is having maximum energy gap? 1 and 2, like this. Okay, is this clear? This statement also? Right. Now again, so today try to be everyone here itself for the study hour also. Why I am asking for study hour? Because we will do numericals. Questions we will do. Okay, so I will make everyone to do at least one question on your own. It means at least one question means, yeah, you are going to do some questions first. Okay, yeah, you got this point? Yeah. Then next one, let us say there is an electron here. What I am saying, there is one electron here. At which level electron is present? At which energy level electron is present? Fifth energy level it is present. Now that electron directly can fall into the ground state. Ground state means what? The lowest energy state. What is the lowest energy state? See, now I am using some terms, you just listen. Ground state means what? N equals to 1. First excited state. Second excited state. Third excited state. Yeah. Third excited state N4. First excited state N2. That difference you should keep in your mind. Okay, don't think first excited state means N equals to 1. No. Ground state means N equals to 1. Okay, is this clear, everyone? Yeah. So now electron is at which level? Fifth level. So that electron directly can fall from fifth level to ground state. Yeah, possibility is there or not? Yes. or electron can fall from 5th level to 4th level, 4th level to 3rd level, 3rd level to 2nd level, or 2nd level to like this. Different possibilities are there or not? 5 to direct 1, 5 to 2, 2 to 1, or 5 to 3, 3 to direct 1 or direct 2. Like that, different possible ways are there or not? Yes. So that different possible ways gives you different spectral lines. What I am saying, different? Yeah. So now we are going to study about spectral lines. Okay. What we are going to study? Yeah, I will tell you about spectral lines. Yeah. See. Are? See, this is a story I am saying you. What I told you, if electron is present at some energy level, if this is a see, listen here carefully. Now tell me where electron is present I am considering. So let us say electron is present here. So electron directly can fall into the ground state, or electron can fall into the 4th state and from here it can come to the ground state, or electron can fall into the 3rd level and from 3rd level it can goes to 2nd level or directly comes to the 1st level, or electron goes to the 4th level, from 4th level it can come to the, or from 3rd to it come to the, already we have written that. Okay, from 3rd to from 4th to 1 we have written here, no, this one, and from here to here we already written, or from directly from here to here. Just check how many lines are there, possible lines. 10 lines we got. Okay, so number of spectral lines possible when an electron is falling from an nth level to the ground state, they will ask you. It depends on which level it is. If it is 5th level, how many spectral lines you got? 10. So all the time you need to count like this. But it is highly difficult now. So let us make one formula here. Okay, so number of spectral lines possible, number of spectral lines possible. So here we have a formula, directly you take this otherwise. So the possible number of spectral lines produced when an electron jumps from higher energy level, that is N2, to the lower energy level N1 is equals to half into N2 minus N1 into N2 minus N1 plus 1. So what is the formula we got? Half into N2 minus N1 into N2 minus N1 plus 1. So let us take our example. What is our highest energy level previously? So 5th level we taken. So from where it is falling, from 5th to ground state, N1 equals to 1. Okay. So now how can you do this? Number of spectral lines, number of possible lines, all possible lines, these are possible lines equals to half into N2 is how much? 5. So ground state N1 equals to 1. So 5 minus 1 is 4 into 5 minus 1 plus 1, 5. So how much it is? See, 5, 10 lines. So same answer we got now, even we are written manually also we got 10 lines, by formula also 10 lines. Is this clear everyone? Yeah. So now I will be asking you one more question, you tell me. Number of possible lines when electron falling from n equals to 5 to n1 equals to 2. From where to where it is falling? 5th energy level to 2nd energy level. How many electrons are possible? Are a simple maths, everyone should answer me this. So how do we do this? 1 by 2 into 5 minus 3. Next, 5 minus 2 is 3 plus 1, 4. So 6 lines we got. Okay, if you want, you can calculate in this. If you want, you can calculate here. From where to where we discussed? 5 to? Once count. 5 to 2 means up to here only lines. 1, 2, 3, 4, 5, 6. Got it? So what is the final formula? Half into n2 minus n1 into n2 minus n1 plus 1. Okay, right. Next. Now, these different energy levels you are seeing now. The first, like this ground state is there now. If that electron is falling from any higher energy state to ground state, what I am saying? Any higher energy state to ground state. All those lines are called Lyman series lines. What is that? Lyman series. N is equals to 5 to 1. I should call that as 4 to 1. 4 to 1. 3 to 1. 2 to 1. Right. From any higher energy state to second energy level. Balmer series. 4 to 2. 3 to 2. 2 to 1. 2 to 1. 3 to 1. 3 to 2. Okay. From any higher energy level to third energy level. Passing series. Any higher energy level to fourth. Any higher energy state to fifth. Any higher energy state to sixth. Hamfari. Like that we have different spectral lines. Hamfari. Okay, up to here is this clear? Yes. So now they will ask you what is the first line possible in Lyman series. What I am saying? First line possible in Lyman series. What is that? 2 to 1. So this is the first line possible now. This is the first line now. So now that is called first line of Lyman series or H alpha line of Lyman series. What is that? What is the second line of Lyman series? 3 to 1. Are you able to follow? Yes, okay. What is the last line of Lyman series? Lyman series. Last line means infinite now. Infinite to 1. You can say it like that. Okay. Now same first line of Balmer series. 3 to 2 or H alpha line of Balmer series. H infinite line of Balmer series. Got this now? Yeah. Next one. Now all this Lyman series, if you want to see, if you see it with your eyes, it won't be visible. Okay? So you want to see them in the UV region. Where it is? UV. So all these Lyman series lines appears in UV region. All these Balmer series lines visible. All this pattern, all this bracket, all this fun line hamper. So all these are IR. This Balmer series, second one is visible, first one is UV. Remember them like this. That's it. Yeah. Yeah. Next one is. See, now electron is falling from second level to first level. We have discussed it like this now. It means when electron falling from higher energy level to lower energy or lower energy level to higher energy, it is moving like this means there is some energy difference we will observe now. How we are going to calculate that? Yeah. So for that you can use this. What is the formula of energy we calculated? We used electron of an nth orbit minus 13.6 z square by n square electron volt per atom. Like that you take it for E1 and E2. make the difference of it, you will get the formula. It means simply I can write delta E is equals to E2 minus E1, which is equals to 13.6, I am removing minus here, directly I am writing, by 13.6 into, see for particular atom means atomic number same only now, so Z square into 1 by N1 square minus 1 by N2 square. Our answer should be in electron volt per atom. So this is for energy difference in terms of electron volt. Okay. So now each each energy associated with some frequency now. E is equals to h nu means each energy is associated with a frequency. Frequency has some wavelength. Yes or no? Yeah. So now you can write E is equals to hc by lambda. Okay. So this 1 by lambda means what you can call? C by lambda is frequency, but 1 by lambda is called wave number. What is that? Wave number. That is indicated with symbol nu bar. So here I have hc, 1 by lambda is there now, that I am writing it as nu bar. So energy is equals to hc nu bar. Energy equals to what? hc nu bar. Okay, right. So now the question, there is one thing called Rydberg's equation. What is that? So that Rydberg's equation is 1 by lambda, which is equals to nu bar is given as RH into Z square 1 by N1 square minus 1 by N2 square. So that's it. This is the final equation you write. What is that? Nu bar equals to 1 by lambda RH Z square 1 by N1 square minus 1 by N2 square. So now this Rydberg's equation constant RH is there, it has some fixed value 1.1 into 10 power 5 centimeter inverse. How much it is? 1.1 into 10 power 5 centimeter inverse. Okay, write this, remaining I will explain the next class. So if you want to practice, you can practice, lot of questions are there here.